Okay, we have here another interesting integral from MIT Integration Bee 2016, problem number 8. We have the integral, the definite integral from 100 to 50 of the floor of log base 2 of x. Okay, I was liking this problem. I like the use of the floor function, and it's a little different than some of the problems that we see. The first thing I want to do is kind of get a sense of what this function looks like. Without the floor, let's just look at what log 2x looks like in this range. First, what we want to do is let's look at just some common values of powers of 2. So 2 to the 5 is 32, 2 to the 6 is 64, 2 to the 7 is 128. And then just putting this in the form of log. So log base 2 of 32 is going to be 5, log base 2 of 64 is 6, log base 2 of 128 is 7. Now we're looking at this function from 50 to 100. So we're looking at, so in here, let's just look at log 2 of 50. So that's going to be between 5 and 6. So that's going to be around, let's just say 5.6. Not too worried about being precise because the floor is going to take care of precision. And then let's look at log 2 of 100. Very similar. That's going to be around, so it's going to be between 6 and 7. So this is going to be around 6.6. So looking at a very rough graph of this thing, just the log 2 of x. We're not looking at the floor function yet. All right. We're looking at this from 50, it starts at 5.6 or around 5.6 and goes to 6.6. So we could, if there was no floor, we could do this and just integrate it and be this area under the curve here. And now that we have some sense of what the graph looks like and what our log base 2 of x function looks like, let's look at the floor function. The floor of y is the greatest integer less than or equal to y. And then let's just look at a couple examples of this if you're not familiar. So, and kind of using what we have here, like if we had something like 5.6, the floor of 5.6 is going to be 5. Or if we had like 5.999, the floor of that's going to be 5. Or if we had the floor of 6, it's just going to be 6. We're already at an integer value, so the function takes us down to the integer below, but only if we're in between integers. If we're already at an integer, we're just staying at that integer. One other example that might throw some people on the floor function is if we have minus 4.3, the floor of this is actually minus 5. And now with that understanding of the floor function, we know that what's going to happen is everything's going down to a lower integer. So if in our graph we have 5 right here, all these values that we're saying are like between 5.6 and 6, all of these are going to come down to here. So our graph of the floor function between 50 and 64, it's going to be just a line at 5. And then similarly, at 64 we're at 6. So between 64 and 100, everything's between 6 and 7. All these are going to flatten out right here at 6. Because the integral is just the area under the curve, we could just find the area of these two rectangles, right? So from 50 to 64, this length here is going to be 14, and this is 5 high. So getting the area of the rectangle, 5 times 14, this piece is going to be 70. Then here, this distance is going to be 64 to 100 is going to be 36. And it's going to be 6 high. 6 times 36 is 216, 6 cubed. And then we just add these two together. So 216 plus 70 is going to be 286. And then we got to see the exact same thing just by breaking up the integral and writing it from, we could have two integrals, one from 64 to 50, and then we'll have another one from 100 to 64. But in this region, we determined from 164, everything is going to be 6. And then from 64 to 50, everything's going to be 5. And so if we just work all this out and integrate 5 and 6, we're evaluating 5x from 64 to 50. And we're evaluating 6x from 100 to 64. But that's actually just these values we found here because we'd have 5 times 64 minus 50 and 6 times 100 minus 64. And if we evaluate this, we just get the same answer, 286. That was MIT 2016, problem number 8. Thanks for watching. Please like and subscribe. Have a good day.